Amplitude modulation, AM, is like a child's swing where the height of the swing the carrier is made larger or smaller by the rhythm of a song, the modulating signal. The carrier is a high-frequency sinusoid that would swing at a constant height if left alone. When we add a song, we change the height of each swing peak in proportion to the audio voltage at that instant. Mathematically, the carrier is C of t equals a C cosine 2 pi fct. The audio or baseband signal is M of t equals a M cosine 2 pi fmt for a single tone example, where Fm is much lower than Fc. A M multiplies the carrier by a factor that varies with M of t. S of AM of t equals a C times 1 plus M, a cosine 2 pi fmt, all multiplied by cosine 2 pi fct. The term M equals a M divided by a C is called the amplitude modulation index. It tells how much the carrier amplitude is allowed to vary. If M equals 0, there is no modulation, just the carrier. If M equals 1, the carrier's envelope swings from 0 up to twice its unmodulated value, the classic fully modulated case. Values above 1 cause overmodulation where the envelope tries to go negative and the waveform becomes distorted, much like trying to push a swing past the ground level. The resulting signal contains 3 separate frequency components: the original carrier at Fc and 2 sidebands at Fc plus or minus Fm. This separation of the audio information into upper and lower sidebands is the heart of a M. Frequency modulation, abbreviated FM, can be visualized as a cyclist who keeps pedaling at a steady speed, the carrier frequency, but varies the speed of the wheels a little faster or slower according to the hills of a road, the audio signal. Instead of changing the height of each swing, FM changes how quickly the swings occur, that is, the instantaneous frequency. If the carrier is C of t equals a sub C times cosine of 2 pi f sub ct, and the audio signal is M of t equals a sub M times cosine of 2 pi f sub mt, the instantaneous frequency of an FM signal is Fi of t equals f sub C plus delta f times cosine of 2 pi f sub mt, where delta f is the peak frequency deviation, the maximum amount the frequency swings away from the carrier. The instantaneous phase, phi of t, is the integral of the instantaneous frequency. Phi of t equals 2 pi integral from 0 to t of fi of tau d tau equals 2 pi f sub ct plus delta f over f sub m times sine of 2 pi f sub mt. Define the FM modulation index beta equals delta f over f sub m. Substituting the phase into the carrier gives the FM waveform. S of Fm of t equals a sub c times cosine of 2 pi f sub ct plus beta times sine of 2 pi f sub mt. The index beta tells how many radians the carrier's phase is being rocked by the audio. A small beta, for example 0.5, means a narrow deviation. The signal looks almost like a pure carrier. A large beta, for example 5 or 10, means a wide swing, producing many sideband frequencies, just as a cyclist on a very hilly road rapidly speeds up and slows down. Explanation: both a M and FM occupy a certain slice of the radio spectrum. The width of that slice is called bandwidth, BW. 2 classic rules help us estimate it. Carson's theorem for AM, sometimes called the M bandwidth rule, is straightforward because a M only produces 2 sidebands. For a single tone modulating signal of highest frequency f sub m, the total occupied bandwidth is simply bandwidth AM equals 2 f sub m. If the audio contains frequencies up to 5 kHz, the AM signal needs about 10 kHz of spectrum. The carrier itself does not add extra width. Carson's rule for FM is a bit more involved because FM creates many sidebands. The rule says bandwidth FM approximately equals 2 delta f plus f sub m equals 2 f sub m times beta plus 1. Here delta f is the peak deviation and f sub m is the highest audio frequency. The rule essentially says, take the frequency swing delta f and add the highest audio frequency, then double it. For a commercial FM broadcast with delta f equals 75 kHz and f sub m equals 15 kHz, the estimated bandwidth becomes bandwidth FM approximately equals 275 plus 15 equals 180 kHz, which matches the 200 kHz channel spacing used worldwide. The rule is generous. The actual power in the far outside bands is tiny, but it guarantees that most of the signal's energy is captured. AM power distribution. Let the carrier amplitude be a C. The carrier power into a load R is a C squared divided by 2R. When a M is applied, the total signal power becomes P total equals PC times 1 plus M a squared over 2. The extra term M a squared over 2 is the sideband power. Half resides in the upper sideband, half in the lower sideband. For a fully modulated signal where M equals 1, the sideband power equals 0.5 PC, so the total power is 1.5 PC. Only 1/3 of that total power actually carries useful audio information, the sidebands. The rest is wasted in the carrier, which carries no information. The efficiency eta of conventional AM is therefore eta equals M a squared divided by 2 plus M a squared. At M equals 1, eta equals 33%. In a double sideband suppressed carrier, DSBSC, system, the carrier is removed, so all transmitted power is in the sidebands and efficiency can reach 100% theoretically. FM power distribution. FM transmits a constant amplitude carrier. The amplitude C does not change with the modulating signal. Therefore, all the transmitted power stays in the carrier regardless of beta. PFM equals a C squared divided by 2R. The audio information is encoded in the frequency shifts, not in amplitude, so the power efficiency of FM is essentially 100%. All power is useful. However, to achieve a large deviation delta, we often need a larger carrier amplitude or higher transmitter voltage, which can make the transmitter itself less power efficient compared with a low power AM transmitter. AM spectrum. For a single tone audio signal of frequency F sub M, the AM spectrum consists of 3 discrete spikes. Carrier at F sub C, amplitude a sub C over 2 in the frequency domain. Upper sideband at F sub C plus F sub M. Lower sideband at F sub C minus F sub M. The sidebands each have an amplitude of M sub a sub C divided by 4. If the audio contains many frequencies, each audio component creates its own pair of sidebands, so the overall AM spectrum is the carrier plus 2 mirrored copies of the audio spectrum. FM spectrum. FM spectrum is richer. Expanding the FM waveform using Bessel functions gives S sub Fm of t equals a sub c times the sum from k equals negative infinity to infinity of j sub k of beta times cosine of 2 pi times open parentheses f sub c plus k f sub m close parentheses t. Each term j sub k of beta is a Bessel function of the first kind. It tells the amplitude of the kth sideband located at f sub c plus k f sub m. Unlike AM, there are theoretically infinitely many sidebands on both sides of the carrier. In practice, for a given beta, sidebands beyond about plus or minus beta plus 1 have negligible amplitude. Example, with beta equals 2, the significant Bessel values are j sub 0 of 2 approximately 0.223 carrier, j sub plus or minus 1 of 2 approximately 0.577, j sub plus or minus 2 of 2 approximately 0.353. Higher orders are less than 0.1 and can be ignored. Thus, FM spreads the same audio energy over many narrow spectral lines, which makes it robust against noise. A small disturbance only slightly changes the phase of each line, but requires a wider channel. Problem 1-AMs. A 1 MHz carrier with amplitude C equals 10 volts is modulated by a 5 kHz audio tone of amplitude at M equals 4 volts. The transmitter feeds a 50 ohm load. A. Compute the modulation index MA. B. Determine the total transmitted power and the power in each sideband. C. Find the required bandwidth. A solution. A. M a equals a M divided by a C equals 4 divided by 10 equals 0.4, 40% modulation. B. Carrier powers. PC equals a C squared over open parentheses 2R close parentheses equals 10 squared over open parentheses 2 times 50 close parentheses equals 100 over 100 equals 1 watt. Sideband power each. PSB equals open parentheses M times a C divided by 2 close parentheses squared over open parentheses 2R close parentheses equals open parentheses 0.4 times 10 divided by 2 close parentheses squared divided by open parentheses 2 times 50 close parentheses equals open parentheses 2 close parentheses squared over 100 equals 4 over 100 equals 0.04 watt. Total sideband power equals 2 times 0.04 equals 0.08 watt. Total transmitted power P total equals PC plus 0.08 equals 1.08 watt. Efficiency eta equals 0.08 divided by 1.08 approximately 7.4%. Low because modulation is shallow. C highest audio frequency equals 5 kHz so BWAM equals 2 FM equals 10 kHz. Problem 2-FM. An FM transmitter uses a carrier FC equals 100 MHz with peak deviation delta F equals 75 kHz. The highest audio frequency is 15 kHz. A. Compute the FM modulation index beta. B. Estimate the transmission bandwidth using Carson's rule. C. List the frequencies of the first 3 significant sidebands open parenthesis k equals 0, plus minus 1, plus minus 2 close parenthesis, and their relative amplitudes using Bessel values for beta equals 5. Assume beta from part A is 5. A solution. A beta equals delta F divided by FM equals 75 kHz divided by 15 kHz equals 5. B. Carson's rule. BWFM equals 2 open parentheses delta F plus FM close parentheses equals 2 open parentheses 75 plus 15 close parentheses equals 180 kHz. Practically a 200 kHz channel is allocated. C. For beta equals 5 Bessel function values from tables are roughly J0 of 5 approximately negative 0.177 carrier amplitude. J plus minus 1 of 5 approximately 0.327. J plus minus 2 of 5 approximately 0.046. Thus the dominant frequencies are carrier 100 MHz, amplitude 0.177 of a C. Upper sideband 100 MHz plus 15 kHz equals 100.015 MHz, amplitude 0.327 a C. Lower sideband 99.985 MHz, amplitude 0.327 a C. Upper sideband 100 MHz plus 30 kHz equals 100.030 MHz, amplitude 0.046 a C. Lower sideband 99.970 MHz, amplitude 0.046 a C. Higher order sidebands have amplitudes less than 0.01 and are usually ignored. These problems illustrate how to move from the theory indices formulas to practical numbers that appear on exam papers.